Hi everyone, we are TAMUK Team 6 from Texas A&M University Kingsville, and our project is titled Origami Inspired Solar Array for a Large Spacecraft. My name is David Balderas, and presenting with me today is going to be Aaron Rocha, Leslie Carrion, Ricky Cuellar, and Mauricio Fernandez. Starting the presentation is the introduction to the project with some background and the project proposal. Large spacecraft usually require a large solar array due to the large power requirement of the vehicle. The size of these solar arrays can pose a problem fitting inside a launch vehicle, but origami folding methods can be used to help improve the stout packing efficiency of these solar arrays. The video to the right shows a conceptual design created by 2014 BYU PhD student Shannon Zerbel. Our project proposal is to design and prototype an origami-inspired solar array that produces 150 kilowatts of power and fits inside the payload bay of the SpaceX Falcon Heavy rocket. Now to summarize the important objectives and design constraints. The primary objectives of the project include the ability to produce 150 kilowatts of power and to fit inside the payload bay of the SpaceX Falcon Heavy rocket. The primary design constraints include a power to weight ratio greater than 28.7 watts per kilogram, a stowed packing efficiency greater than 26.3 kilowatts per meter cubed, and a total weight less than 63,800 kilograms, which is the low Earth orbit payload capacity of the SpaceX Falcon Heavy. Shown here is an outline of all the work that will be presented today. First, we have the mathematical model increase pattern, followed by the solar array assembly. Then we will talk about the actuation, solar panel assembly, prototype, and then end with the conclusion and future work.
Mathematical model increase pattern, we chose to use a flasher folding pattern because of the volume constraints for the vehicle payload. We did consider an accordion folding pattern that is currently used on the ISS, but due to the flasher's 10-time increase in deployable diameter to folded diameter, we determined it was the optimal solution. We used a Mathematical 12 notebook that sets up the constraints for a general flasher and solves for vertex coordinates for both the crease pattern and the folded form, as you can see on the picture on the top right. On the bottom right picture, you can see that M, highlighted in green, is the number of sides of the central polygon that the pattern will wrap around, so 4 for us. H is the number of axial bands between the bottom and top of the folded cylinder, which is highlighted in purple and yellow, that is 2 for us. And R is the number of rings on the pattern, that was only 1 for us. You can also see in the picture that the mountain folds are indicated with solid red lines, while valley folds are indicated with dashed blue lines.
Now we will discuss the solar array assembly. The CAD model shown to the right is the design created by TAMUK Team 6 in SOLIDWORKS. It showcases the 3 sub-assemblies, which include the kinematic structure, along with the solar panel assembly, and the connecting linkage mechanism, which ties in the solar panel assembly with the kinematic structure.
The first subassembly we will talk about is the kinematic structure. This structure is responsible for supporting the weight of the other subassemblies and deploying the solar array once it's in space. The structure expands to 573 meters squared to allow for the fully deployed solar array and connecting linkage to fit within it. The structure also retracts to 0.35 meters squared to fit inside the payload bay of the Falcon Heavy rocket. The structure will be made out of aluminum 7075-T6, which will give us an estimated 12,500 kilogram weight. Our initial iteration allowed full range of motion, but impacted our ability to retract because of the connectors protruding. An example of a protruding connector is circled in red. This flaw was corrected in our final iteration while still allowing a full range of motion.
Next, we'll talk about the connecting linkage. The connecting linkage is used to connect the solar panel assembly to the kinematic structure by tying each corner of the solar panel assembly to 4 individual connectors on the kinematic structure. The linkage allows for the necessary motion by means of a universal joint between each link and a revolute joint that connects the connecting linkage to the kinematic structure. The detailed design for this mechanism is still being in progress. The solar panel assembly will now be discussed. The image in the top right hand corner is a layout of our 21 by 21 meter solar panel assembly. The gap size between each panel is a total of 6 times the thickness of the entire solar panel. Theoretically, mountain folds and valley folds are used in origami models with thicknesses, but after iterating our prototype, we discovered that having a gap size of 6 times the thickness allowed for much easier folding, and this is why we decided to go with a gap size of 6 times the thickness. The image in the bottom right-hand corner shows this gap size in the CAD model.
For the actuation, we'll be using an electrical motor that will be expanding and contracting the solar array in 1 degree of freedom. We'll be using 4 rotary actuations that will be attached to the cross-sectional links of the areas that the arrows are pointing to in the figure below. For the table, we have yet to decide the type of actuation we are using, but the 3 we are considering are the Ultra Performance, the Enhanced Type 5, and the High Torque Type 5. We chose these 3 because of the operating temperature, the wide range operating temperature that it has, and the amount of torque it produces.
The solar array will have a total of 21 solar panels and will have a surface area of almost 475 meters squared to produce the desired 150 kilowatts of power. Each panel will have the same 4-layer configuration, which can be observed in the image to the right. The overall thickness of each solar panel will be 0.26 millimeters, which will cause it to weigh 442 kilograms. The flexible membrane, which will hold all of the solar panels together, will be made of a Kevlar cloth and will be sized accordingly to withstand all possible experienced loads. To determine the required Kevlar membrane thickness, many FEA studies were performed on SOLIDWORKS while varying several different parameters. After multiple trials, we obtained the most favorable results when the membrane thickness was 4.5 millimeters with hole diameters of 0.75 meters. As a result, this would make the entire solar array assembly, both solar panels and flexible membrane included, almost 4.8 millimeters thick and weighing about 3,578 kilograms.
For our weight budget, we calculated the weight of all the components in our design by multiplying the material's density with the volume. We got a total weight of 22,134 kilograms, which is way below the constraint of 63,800 kilograms of the Falcon Heavy rocket for low Earth orbit payload.
We created a small prototype of the Origami solar array using a 3 mil Kapton sheet and various 3D printed components. The components included 1 millimeter thick solar panels, 1/4 inch thick links, and custom connectors for the kinematic structure. The hardware to fix the links and connectors were slotted spring pins of 1/4 inch diameter. The actual assembly of the prototype will be discussed in the next slide. The assembly of the prototype began with the Kapton membrane and 3D printed panels. The membrane and panels were joined together using a thin layer of Gorilla Glue. The panels had a gap of 6 times the thickness between each panel to facilitate folding. Through testing, we discovered that this was a good gap size, and we also implemented the use of stress relief holes based on some advice from Dr. Zerbel. The kinematic structure was put together by hand with the use of pins. We ran into some trouble with the quality of our 3D printed links, but this was quickly resolved by changing to a different spool of PLA material.
In conclusion, the Origami solar array assembly designed was able to meet the spatial constraints to fit inside the SpaceX Falcon Heavy payload bay and generate 150 kilowatts of power. Unfortunately, a solar array mechanism of this size did not meet our power to weight ratio and stowed packing efficiency constraints, which are taken from the ISS solar array wings. This is most likely because of our use of only 1 ring for the 4-sided flasher crease pattern. The team switched from 2 rings to 1 ring on the crease pattern to allow for simpler and easier to simulate motion. Reducing to 1 ring caused for a solar array mechanism that was too heavy and had too large of a stowed volume. One of the most important lessons learned is that an origami flasher solar array's performance is greatly reduced when using only 1 ring of the origami crease pattern.
Some aspects of the project that can be optimized and improved include implementing a different flexible membrane to our design, the addition of a metal frame to the solar array along with an increase of the attachment points on the flexible membrane, providing a more detailed design of the connecting linkage and testing its functionality, improving the rotation ability of the links on the kinematic structure, and reducing the weight of the solar array mechanism overall.